In this chapter, we will look at an example of a typical acceleration, braking forces for rim brakes and disc brakes, models for comparing rotational moments, detailed torque and force calculations for disc brakes, some good and bad disc brake wheel designs, and we'll call that part 1 because there's more to come, and an example of a rim failure.
When for a new bike you are shopping, the physics of starting and stopping should be clear in your mind. Don't go into it blind. Some facts I will show are jaw-dropping. This chapter will go into the physics of acceleration and deceleration, and particularly the deceleration of bicycles with disc brake wheels.
First, looking at acceleration, this is obviously a rim brake wheel. If it were a disc brake wheel, the physics of acceleration would be pretty much the same. Newton's second law of motion tells us that if we put a forward force on the bike, that will be equal to its mass times acceleration. Mass is equal to the mass of the rider and the bicycle added together, and A is the rate of acceleration. Here's my rim brake situation. Let's say I have a rider with a mass of 100 kilograms, a bike 10 kilograms, total mass 110 kilograms, and my rider pedals with an average power of 200 watts. How long will it take him to reach 20 miles per hour, and what will be the average rate of acceleration? Well, 20 miles an hour is 8.94 meters per second in the SI system. This, you will recall, is our formula for the total kinetic energy, where B and C represent the mass of the bike and cyclist, and R, T, and T represent the mass of the rim, tire, and tube. Substituting the given values for the mass of the bicycle and cyclist as well as the rim, tire, and tube gives me this. Multiplying out that first term converts 110 kilograms into 55. Now I can consolidate a little bit. If I consolidate my mass terms and factor out V squared, I get this. Now V, remember, is 20 miles per hour, which is 8.94 meters per second. And when I substitute 8.94 meters per second for velocity, I get this term here. When I multiply that out, I get first this expression and then this one. And kilogram meter squared per second squared is the unit of joule. So my total kinetic energy is 4.44 times 10 to the third joules. Power is the change in energy divided by time. A watt is a joule per second. Second equals joule divided by watt. Time is my change in energy divided by power, and the time works out to 22.2 seconds to accelerate to 20 miles per hour. The acceleration rate on the average is the change in velocity divided by the change in time, and that works out to 0.402 meters per second squared. That's clearly a simplification of the calculation because I ignored, amongst other things, aerodynamic drag, but still it gives us an idea, and our real goal here is going to be to compare the issues that we face when we stop the bike anyway. If I wanted to be more precise, I would plot a graph of velocity versus time, and at constant pedaling power, I would see that my velocity would increase non-linearly because, amongst other things, I have an opposing force that gets larger in the form of aerodynamic drag. Then I could calculate my instantaneous velocity at any point on the curve by taking the first derivative of velocity with respect to time, which would be dv dt. But we don't need to use calculus because we said that this number here is quite sufficient for our purposes. If we're rolling along with an energy of 4.44 times 10 to the third joules and we want to stop the bike in 3 seconds. We want to look at the scenarios for stopping the bike with either rim brakes, as we see here, or disc brakes. For either rim brakes or disc brakes, this is our picture starting at 8.94 meters per second, 1001, 1002, 1003.
Kinetic energy is power times time. There's my kinetic energy. Power times, I'm going to stop the bike in 3 seconds. My stopping power is 1480 watts. Now, for the time being, let's assume that that is distributed equally between the two wheels, which gives us 740 watts per wheel. My acceleration is the change in velocity divided by the change in time, and I'm going from 20 miles an hour, which is 8.94 meters per second, to 0 in 3 seconds, which gives me a rate of deceleration of minus 2.98 meters per second squared.
My stopping force is going to be mass times acceleration, which is 110 kilograms times negative 2.98 meters per second squared, and that equals a negative 328 newtons total, of which I will distribute that for now equally to each wheel, and that gives me a negative 164 newtons of reverse force that has to be applied at each wheel to stop the bike. So if I'm rolling along at 20 miles an hour or 8.94 meters per second, and I want to go from that speed to this speed in 3 seconds, I have to apply a force in the opposite direction of 164 newtons per wheel. Newton's second law of motion applies here also, except that here, since we're slowing down, the acceleration term is going to be negative, and if you want to, you can call that deceleration. There are only 3 places where anything actually touches the wheel. Here at the hub, here where the brake caliper contacts the rim, and down here where the wheel contacts the road surface. We're using the front wheel as an example, and we're simplifying the discussion by assuming that the braking occurs at this point here, directly above the hub. Using the convention of showing horizontal movement in the x-axis, we have a force here on the hub exerted by the fork of the bicycle to the right in the x-axis by the hub, and up here I have a force to the left, also in the x-axis from the brake, and a second one down here from the surface of the road. The force on the hub is equal to the sum of the two opposing forces, which means that the sum in the x-axis of all the forces is equal to 0. To allow us to see the effect of the force at the brake and the force at the surface of the road, I'm going to turn this wheel 90 degrees counterclockwise. Doing that will allow me to use a pictorial analogy that may be useful. That gives us this picture here. These two forces are equal, and they both operate at a distance from the hub equal to the radius of the wheel. Let's use an analogy of this simple seesaw here, which turns within this circle. The turning direction is, as we can see here, on the right and left of the seesaw. The child on the left is sitting at radius r from the fulcrum, so is the child on the right. The force of the child on the left is equal to the force of the child on the right. In one case, the turning direction of the seesaw is clockwise, in the other case it's counterclockwise, but the sum of these two turning moments is equal to 0. So here is the wheel back where it was, with the seesaw shown on its side. So going back to our wheel, we see that the sum of the turning moments here is also equal to 0. The force of the brake in the x direction here times radius r is equal to the force of the surface of the road in the x direction also times, again, the same radius r. So the force at the brake is equal to the force at the road. A small amount of distortion of the wheel actually accompanies this braking sequence. When I brake, these two forces pushing to the left will cause the fork to push the hub to the right, and my wheel, which was shaped like this, will become distorted slightly and look like this. With disc brakes, I'm stopping the hub, but the wheels want to keep turning because of the rotational energy in the wheels, as well as the translational kinetic energy of the bicycle and the rider, and we have to apply some pretty large countering forces to stop the wheels from turning. To understand this, we'll go through the same analysis as we did with rim brakes, and I'll also discuss with you a little bit of the geometry and trigonometry that applies. With disc brakes, we have to also obey Newton's second law of motion. And we see this analogous picture, and I'll come back to this in a minute and derive this, but I first want to discuss the braking sequence. When I slow or stop my wheel, my stopping torque transfer sequence is as follows. First step is a force is applied by the disc brake caliper to the outer part of the rotor, and then step 2, the torque is transferred to the hub. And then the torque is transferred to the rim by the spokes, and the spokes actually attach here to this imaginary ring, and this is the ring where the holes are located, and it's called the whole flange circle, and the diameter would be the whole flange diameter. Even though this torque transfer doesn't really occur sequentially, it's still useful to think of it that way. Step 1 here, step 2, and step 3. Because the spokes attach to the hub flanges and not the rotor, the torque transferred from the hub to the rim is independent of the rotor diameter. But the hole-to-hole flange diameter is important. So if we compare these two wheels, we see that the first two steps of the sequence are important in terms of the diameter of the rotor. But in the third step, where the torque is transferred by the spokes from the hub to the rim, the whole flange diameter is important, but the rotor diameter is not. When we start to brake with a bike with disc brakes, the momentum of the bike puts a forward force on the hub through the fork, just as it did with rim brakes. There are two opposing forces in the wheel, one applied down here at the surface of the road, and that is applied at a distance r, and another one from the brake, which is applied here at the whole flange diameter at a distance of small r. The sum of all the forces in the x direction will again be equal to 0, and that means that the force at the hub is equal to the force at the brake and the force at the surface added together. The sum of the turning moments will be 0 again, which means that the force applied by the brake here at radius r is going to be equal to the force applied at the surface times big R, which means that the braking force applied at the hub is equal to the braking force applied at the road times the ratio of big R to small r. Let's rotate this 90 degrees to the left and once again use the seesaw analogy. That gives us this picture. We'll move it over here. And here is finally our seesaw, and obviously if the seesaw is going to be in balance, the child on the left has to be much larger than the child on the right in order for the turning moments to be equal. The braking force at the hub applied by the brake is going to have to be much larger than the braking force at the tire applied by the road surface. Let's expand our view beyond just the wheel and look at the braking forces on the bike and rider altogether. Dimension B here is the length of the wheelbase. Point C is the center of mass or gravity of the rider and bicycle combined. Y is the height of the center of mass above the ground. X is the distance from the rear hub to the center of mass, and B minus X is the distance from the center of mass to the front hub. The forward force from the center of mass is mass times acceleration. The vertical force on the center of mass is also mass times acceleration, but in this case, acceleration is the gravitational constant g. Point R, indicated by the red dot, is where the rear wheel contacts the ground, and the force there going to the left is the force at point R in the x direction. This is the analogous force on the front wheel. And lastly, at points F and R, we have the force pushing up from the ground opposing the downward force of gravity. We can write a number of equations from this diagram, and the first is this: mass times acceleration equals the force on the rear wheel in the x direction plus the force on the front wheel in the x direction. This force equals this force plus this force. I could also write the equation that way, and that means that the sum of all forces in the x direction is equal to 0. The next three equations will show us the sum of the turning moments at 3 points: at point R, point F, and the center of mass. In each case, the sum of the turning moments is 0, as shown by these equations, and there's one bit of information we can glean from these right now. And that involves looking at this equation here, which concerns the turning moments around the front wheel. The turning moments on the front wheel around point F have to be within this circle that has a radius of the wheelbase B. More limitedly within this arc. When I have to brake hard, I have a very large mass times acceleration. I have to have a large stopping force provided by my brakes. This causes the center of mass to shift forward and the weight on the rear wheel to go down and the weight on the front wheel to go up. And that causes most of the braking to be done at the front wheel. This happens when I have either disc brakes or rim brakes, but with disc brakes, my brakes are more powerful, so this forward shift can be more pronounced. If I'm not careful, I can find myself going from this to this to this to this.